Okay, so hey everyone. Today I'll be doing the chemistry AMS for week 1 of term 2. So we start with question 1. Recognize a diprotic acid. Okay, which of the following are diprotic acids? Now, a diprotic acid is something that has two hydrogens. So H2, maybe H2S, maybe H2SO4, which is there, maybe hydrogen carbonate, whatever. So you just look for whichever one has H2. This one has H3, so no. This one has one H, and this one has one H. These two have two hydrogen atoms or molecule. Yeah. So H2CO3 and H2SO4 are your answers. Okay. Which of the following is a not ionic of neutralization reaction? Neutralization reactions between an acid and a base, any acid and base to produce a salt, or not necessarily a salt, just it has to be between an acid and base. Okay, so here iron isn't an acid or base, it's an element. This is an acid, there isn't a base here, pointers. So this is wrong. Same thing here, this is water, this isn't an acid or a base. Though we have an ACl, which also isn't an acid or a base. Ca and Cl2, no acid or base here. And here you have HCl and H2O. Now H has an acid, but H2O isn't a base, so it's not neutralization. So that leaves our only option with H plus and OH minus gives H2O. And this is obviously like a neutralization reaction, because what's the definition of acid? If it has H plus, that's an acid. If it has OH minus, it's a base. So here we have both. Now they might give it to you as like KOH plus HCl to make what would make H2O and KCl. So it would make like this KCl plus H2O. Now this is a neutralization reaction because you have the base, the OH here, and you have the acid here with the hydrogen molecule. So yeah, okay. Moving on, question 3. Which of the following could be used to prepare soluble salts? The addition of an acid, the action of an acid upon a metal, the action of an acid upon bases, and the action of an acid upon the basic metallic oxides. Now, salts, you see base upon an acid, base upon basic whatever. If it's acid and a base, straight away choose it to make soluble salts. Most of the time, it's like that. Um, for this one, I'd memorize the action upon a metal because it's correct and it doesn't follow the rule I just told you, but it's a property. Okay. Now, question 4. An aqueous solution of hydrochloric acid HCl is added to lumps of calcium carbonate CaCO3. What's the following is an expected observation: effervescence or formation of bubbles. Now, this is for a good reason, because if you actually do this equation, HCl plus CaCO3, this goes into being hydrogen carbonate and CaCl. CaCl, we'll leave it alone. I don't really need it. The hydrogen carbonate, so HCO3. This is what I'm concerned about right now. This CaCO3, wait, I mean CaCl, you can leave it because you don't really need it right now. Plus hydrogen carbonate. That's HCO3. Okay. This dissociates into water, so H2O, and carbon dioxide. Okay, now this, I don't think this is balanced, but it dissociates into that. Now, um, what do we do now? What are the products for the net ionic equation of the reaction? H2O and CO2. Those are your final two. Now you can, in the written, you can, I think you can directly skip the HCO3 and just write uh, H2O and CO3 if they give it to you in the written part, but I don't think they'll even bring this in the written part. So, question 5. Ammonia and electricity is produced industrially from nitrogen gas and hydrogen gas by a process called the Haber process. This is the equation of the Haber process. Which of the following conditions are needed for the optimum yield? Do you memorize this? It's been asked so many times. So the pressure is at 200 atmosphere or 20,000 kilopascal. if you remember, one atmosphere is equal to, I believe, 100 kilopascals. Okay, let me just make sure. So you cross out these two here, you cross out these two here. Then you divide by two. Yeah, 100 kilopascals. Yeah. So if they ask it to you in pascals or kilopascals, sorry, you remember this. One atmosphere is 100 kilopascals. Okay, and now the temperature for both the Haber process and the contact process is 450 degrees Celsius. Always remember this. The catalyst used in the Haber process is iron. The catalyst increases the rate and has no effect of the yield of ammonia. First of all, this came in the diagnostic today, and you should generally know just the catalyst. You memorize this first part, and the second part you should know. And even if you don't know it, it's basically logic. Okay, sulfuric acid, H2SO4, is manufactured industrially by the contact process. After reacting molten sulfur with air in a large furnace, the SO2 gas produced is mixed with more air to make product A under certain conditions of temperature and pressure. Give the chemical formula for product A. This is product A. We don't really need all of this given, honestly. We only need the first part. So SO2 plus O2 gives product A. You memorize that it gives you SO3. Okay, just memorize it. There isn't really a way for me to explain it. Okay, what are the conditions? So first of all, temperature is always 450 degrees Celsius. And remember, one atmosphere is 100 kilopascals. So two atmosphere, you multiply by two on both sides, 200 kilopascals. Okay. The catalyst is vanadium oxide, which, just in case they do ask you, it's highly unlikely they will. The chemical formula of vanadium oxide, because it wasn't a past paper for the final, they didn't bring it, but you never know, is V2O5. Just remember it, sorry. Okay. Question 7. Select the weak acids. This is memorization. Hydrogen chloride is a strong acid. This is a base. An AOH is a base. Hydrogen nitrate, you don't really need to worry about it, but it's a strong acid. So you have any organic acid. So if it has COOH, this means it's organic. And organic acids are weak. Okay. H2SO3 and H2S. Just remember those. Select the strong bases. Now this one, they made life really easy for you because they only have two bases here anyway. This is an acid, this is an acid, this is a weak acid, we said it, and this is another acid. So it's literally only these two. Okay, question 9. This came in the diagnostic today, and please remember it because 90% they will ask it to you in the AMS tomorrow as well. I did have a diagram of all of them drawn in a previous video. I'm asking about all of them, discussing all of them, but I don't have it anymore. I don't know where it is. Okay, anyways, we'll just recap here. MgO is basic. CO2 is acidic. CO. Now there's a general rule. Oxides. Let's say they're all oxides. Okay, they can be basic. They can be acidic. I'll say AC. They can be amphoteric. They can be neutral. Uh, they're in a previous video. The last chemistry AMS or whatever I recorded. Just recap there, take a look at it, and then you'll figure it out. Basically, if it's metallic, if it's a metallic oxide, it's basic. Okay, if it's non-metallic, so NM, it's acidic, and amphoteric and neutral have their exceptions. Al2O3 and zinc oxide, amphoteric, along with the third one, and neutral, CO, N2O, and I believe there's another one. I don't remember, but I will recap this later at the end of this video, hopefully, if I get to see that diagram. Whatever, we can apply what we learned now because they don't ask you about the specific ones. MgO, Mg is a metal, magnesium, basic. CO2 is acidic, CuO is basic because copper is a metal. N2O is one of the neutral oxides. It's one of the exceptions to the acidic rule. CO is another neutral one. Amphoteric ZNO, SO2 is acidic, and Al2O3 is amphoteric, and calcium oxide is basic because they're metals. Okay. This came in the diagnostic, but with the names. So it was the exact same answers. A is acidic because it has a P. Let's just do a quick recap of the pHs. Anywhere below 7. So let's say it's blue. Anywhere here is acidic. Okay. Anywhere greater than 7. So let's go, let's put it black. This is gonna be basic. Okay. So choose the nature. A is acidic because look, it's below 7, and obviously at 7 it's gonna be neutral. B is neutral because B is at 7. B is at the 7 mark. C is basic because C is greater than 7. As you can see, it's at 9. And D is basic because D is at 12, which is greater than 7. Okay, question 11. A student asks to find the OH minus, the concentration of OH minus of a hydrochloric acid solution, HCl, whose pH is 5.36 at 25 degrees Celsius. Okay, for this one, you're gonna need to know that the pH, that the concentration of hydrogen is equal to 10 to the power of negative pH. And I believe if you calculate it as an equation solver, you can apply the formula pH equals to negative log base 10 H plus. If you calculate it as an equation solver though. If it doesn't, I'll be teaching this way is actually really easy, so it's fine anyway. So let's do it. The concentration of H plus is 10 to the power of negative 5.360, which means, let's do this on a calculator. 10 to the power of negative 5.360, but we don't need to write that. 4.3, whatever, this, all of this, so 4.365 times 10 to the power of negative 6. Okay, now, again, you should remember this formula. OH minus is equal to 10 to the negative 14 over H plus, the concentration, of course. Okay, and again, they're interchangeable. So you can put H plus here, and you have to put OH minus there to find the concentration of H plus. So now what we're going to want to do, 10 to the negative 14 over our answer. Where's the answer here? Which is 2.29 times 10 to the power of negative 9. And this is our final answer. Okay, moving on. Question 12. Same concept. This one's actually easier though because you don't have the pH. So you have this acid H2A. Okay, now it's point 0.4 moles or 0.4 molar. Now you're gonna want to write the dissociation reaction for this to find out how many moles or how many molar, what's the concentration of each one. This is basically, it's a dumb process, and a computer part, don't do it like this. Don't just write the dissociation reaction. I'll teach you what to do. So this dissociates into 2H plus and plus whatever A, element A, or we don't know what element A is, A2 plus. Okay, so now you have 0.4 here, so 0.4. What you do is you multiply 0.4 by the coefficient. So 0.4 times 2, which is 0.8. And here 0.4, but this we don't really care about. Or if you're in a computer part, just straight away multiply this by the subscript of hydrogen or hydroxide, depending on the question. So here 0.400 multiplied by the subscript, which is 2, so 0.400 times 2 is 0.8. So you write down your scientific notation to three significant figures. You write down 8.0. I don't remember if I wrote it. I wrote it as 0.800. Now you can write it, I believe, as 8.00 times 10 to the power of negative 1, because this is actually the answer. This is supposed to be the answer, according to what they want us. They want us to do. Sorry. Three significant figures. This is three significant figures. I don't know why they said in scientific notation and they didn't follow their own rule here. Now you do what you did before. Same thing. 10 to the negative 14 over the concentration of H plus. So over 0.8, which gives you 1.25 times 10 to the power of negative 14, and that's your answer. Question 13. Calculate the concentration. Okay. This is easy, fairly easy. So you multiply this by the subscript to get the hydroxide. The subscript is 1 here, so 0.060 stays. So the concentration of OH plus or H minus, sorry, equals to 0.06. Right? Now you do literally the same thing we've been doing for the past 3 questions. So here's 0.06. 1.666 repeating times 10 to the power of negative 13. Two significant figures, so 1.7 times 10 to the power of negative 13. Okay. A student is asked to find the pH of the solution. In an experiment, he prepares an aqueous solution of hydrochloric acid by dissolving 0.08 moles of the acid in a 250 whatever. Here you're gonna apply N equals CV. Let me just fix this N. So N equals CV. What's our N? N is 0.08 equals to the C is what we want to find, and this is in milliliters or centimeters cubed. You want to change this to liters or decimeters cubed. So the conversion factor between centimeters cubed and decimeters cubed, or milliliters and liters, they're the same thing. Decimeters cubed and the liter are the same, and centimeters cubed and the milliliter are the same. This is times 10 to the power of negative 3. So times 10 to the power of negative 3 to change. You divide by 1,000. So 0.25, because you did 250 times 10 to the power of negative 3. So I'll just write it like this, which gives you 0.250. Multiplied by our concentration. So to find C, you divide both sides, so 0.250 here and 0.25. What you do now, you do it on the calculator. 0.08 divided by 0.25, which gives you 8 over 25. Thank you. 0.32 or 0.320 to three significant figures. So 0.320 molar. Now deduce the pH. This is the concentration. And so now you apply the pH equals to negative log base 10, or just log on a calculator, the concentration of hydrogen ions. So just, there we go. Okay. So negative, so you do it now, you have your concentration 0.32. So negative log, which our answer, which gives us 0.4948 or 0.495 to 3 decimal places. Now, okay, so question 15. The best method to obtain zinc sulfate solid when H2SO4 reacts with zinc oxide is crystallization. Why? Because I made a flowchart here. Salt preparation. First you start, is the salt soluble? Yes or no? If not, it's precipitation. If yes, it's the reactions with acids. And are your starting materials soluble? If yes, use titration. If not, you use the access method. Okay, feel free to screenshot. It's a really good flowchart. So I'll just remove this. Okay, now so here the answer is crystallization, even though it's not mentioned in this flowchart. Why? Because zinc sulfate. Now, if you remember from your solubility rules, sulfates are mostly soluble except with lead, calcium, and barium. Zinc sulfate is not part of lead, calcium, or barium, so it's soluble in water. Now, precipitation, if you notice here, it says, is the salt soluble? If not, use precipitation. Now, the salt is soluble because H2SO4 is highly soluble in water, so precipitation straight away. Is out straight away. Okay, why can't you use the access method? Because the access method, according to external sources, ChatGPT, the reason why it's insoluble because if you use it, you're gonna have leftover acid and it's gonna be impure and you're gonna need more steps to remove it. If you add excess zinc oxide, the zinc oxide will remain in the mixture and it will need to be filtered out, which is less efficient. So it's not the best solution. And here, this is also going to take longer because then you're going to need additional steps to neutralize it and remove it. So it's not that good of a solution. So your only other method is titration and crystallization. But titration, I won't really say it. Mention crystallization. Just say crystallization. It's a dumb question. Anyway, they probably won't bring it. But you never know. Question 16. A mixture of NH4, NO3, and NOH solution are heated. A gas with pungent is released. I think they meant pungent smell. Uh, the gas turned wet litmus paper blue. You should know this that NH4, whenever you have NH4 and NaOH, just remember you're gonna have ammonia straight away. Just remember NH4, whenever you see NH4, just know you're most likely gonna have something to do with ammonia. Okay, and once you see pungent smell, it confirms it. خلاص يعني you're confirmed that pungent smelling gas is produced. That's it, it's ammonia. So first you answer part B, the gas produced is ammonia gas, and the gas turns wet red litmus paper into blue litmus paper. Tongue twisters. Okay, question 17. To prepare PbSO4 salts, equal quantities of PbNO3, uh, 2 and Na2SO4 are mixed in water. Insoluble salts are prepared by precipitation. Remember, I just mentioned this. If you have SO4, it's soluble with most everything except Pb, Ca, and Pa. Pb is lead, and here you have that. So this is gonna be done by precipitation. It's an insoluble salt. Now, I don't have the options, but it's the most common like logic, I believe. I don't know. The options seem very like if you combine these two, like it's obviously gonna make PbSO4. I don't really know how to explain it. I need to see the options. Anyways, when a strong acid and a strong base react in quantities that contain equal numbers of mole is H plus and OH minus, a neutral solution is produced. Obviously, because if they're equal moles of an acid or hydrogen and equal moles of base or hydroxide, they're gonna neutralize. Okay, a neutral salt can be prepared by mixing a strong base with a strong acid. Again, neutralization reactions form neutral salts. Okay, a salt solution is made by adding sulfur trioxide to water. Keep in mind, this is adding sulfur trioxide to water, so it's originally 7 changes into 1. Okay, not water to sulfur trioxide. Keep that in mind, because this is probably going to confuse people. Okay, this is the same question. I think it's not sodium. Yeah, okay, whatever. Oh, there it is. Okay, when HCl solutions added to calcium carbonate, CO2 gas will be produced. Obviously, what I would do, HCl. Now you memorize this. Really, there's no other way of memorizing it. Carbonates always give off carbon dioxide. Just remember them. Question 22. If my internet, thank you. When sulfuric acid solutions added to sodium sulfite, uh, SO2 gas will be evolved. Now there's like 7 equations you're gonna need to memorize. Just memorize this. If you have sulfite and sulfuric acid, whatever, you're gonna have SO2. Because remember, sulfite's SO3. It doesn't even need to be sulfuric acid. It can be HCl plus, for example, NaSO3. This will give out. This will react to form. I think this will react to form sulfur dioxide. Okay. When KOH solutions added to NH4Cl and the mixture is heated, the gas NH3 will be evolved. Again, NH4, think ammonia, think NH4, and then أكيد you need a base. So this is the end of the quiz. Good luck, everyone. Happy start of term 2, even though they stole our holiday from us.